Right, so this conjugation and its properties come from molecular orbital theory. So let's go ahead and take a look at the molecular orbital theory of some of these conjugated pi system. And so remember the difference between molecular orbital theory and just our hybridization or just looking at the orbitals of a lone element is that molecular orbital theory says that atomic orbitals mix to form molecular orbitals. So these orbitals no longer belong to one specific atom. Instead, they belong to the molecule as a whole. And so what we're interested in here is our pi bonds that come from p orbitals. So let's take a look at two p orbitals mixing, right? So we've got a p orbital right there with an atom in the center, and then another one over here. And they're each going to have one electron in them, and then they're going to mix together. And when they mix together, they're going to form a lower energy state and a higher energy state as well. This lower energy state is going to be a pi bond. This higher energy state is going to be an anti-bonding orbital or a pi star bond. And so if we take a look at the way it can mix positively to make a bond, these two oranges and the two purples will be in phase with one another, and so they will mix with one another. So we'll have one kind of big orbital above and below, right, to make our one orbital. And you can see how it looks like those two orbitals mixing together. When we go up in energy or go up to the next orbital, we insert nodes into this. And so we have our two nuclei here, and then in between them, we have a node. And so this node represents 0 electron density. And now our orbitals are going to be flipped, right? Now the purple and the orange are on opposite sides of one another. And you can see how that doesn't really look like a bond, right? It doesn't look like the atoms are connected to one another. And so then when these forms, these molecular orbitals, the two electrons from both sides will now go to the lower energy state, right? And so that's the whole point of mixing. Why do these orbitals mix? It's to get to a lower energy state, right? So by mixing, the electrons can go into an overall lower energy state, right? And why do they want to go to an overall energy state? It's the same reason everything else wants to go an overall lower energy state, right? If you think about a ball, it's going to roll down a hill if it can. And so the same way the ball goes to the lowest potential energy, these electrons and their orbitals mix together to find a lower energy state. And so that in that example, we had two pi orbitals, but then when we have a conjugated system, we have at least two pi bonds, which are 4 p orbitals, right? So this in this case, this is butadiene. And so here we have 4 p orbitals. And so we can think about the way they'll mix together, right? So we'll have 4 p orbitals. And the number of molecular orbitals will always be equal to the number of atomic orbitals. So we've got 4 p orbitals, which means that we're going to form 4 molecular orbitals as well. 2 of them will be bonding, 2 of them will be anti-bonding. And so and then as we go up from down to the top, we'll insert more and more nodes. So in this first one here, we have no nodes. And so it's just a big old orange on top and purple on the bottom, right? Everything is in phase. And so this represents that the electrons here are delocalized over this entire molecule, right? And so you can see that our central carbon-carbon bond here has essentially a double bond. Then when we go up, we insert one node. And in this case, we're going to insert it between these two nuclei. And so on this side, we'll have these kind of bonding arrangement over here. And then on this other side, we'll have the opposite kind of bonding arrangement. And then if we think about what that means for our molecule, here now our electrons are localized onto just the external double bonds. And so you can see the central carbon-carbon bond has some single bond character as well, which is what we saw from the bond lengths as well, right? The central carbon-carbon bond length was not as short as the external carbon-carbon bond lengths. And then when we go further up, we insert more nodes. So in this case, we have 2 nodes. And so we'll do the central one's kind of like a bonding type of thing, but then the 2 outsides are not bonding. And then finally, for this 4th one, we'll have 3 nodes. And so none of these will bond with one another. And then if we think about, we have 4 p orbitals here mixing, so we've got 4 electrons, and so they'll fill out these lower 2 electron levels, right? And so you can see by mixing, the 4 electrons have gone down in energy. And that's what it's all about, right? And so this molecular orbital theory explains the stability and the bond lengths of butadiene. And you can expand it further. For example, you could add another pi bond, and you get hexatriene, right? So now we've got 1, 2, 3 orbitals, or 3 pi bonds, which means 6 p orbitals. So you can see we have 6 molecular orbitals, and you can see at the beginning they have 0 nodes, then 1 node gets added, then 2, then 3, then 4, and then 5, right? And then the electrons fill this lower half, and you can see they would be lower in energy than where the atomic orbital would be, right? And these lower ones down here are the bonding, whereas these upper ones here are the anti-bonding. Another thing to know is that this lower energy, or this highest energy filled state, is called the HOMO, or the highest occupied molecular orbital. And then the lowest energy unfilled one is called the LUMO, which stands for lowest unoccupied molecular orbital. And later on, we'll explore this energy gap here, because this energy gap is going to give these conjugated systems some unique properties. And that's because this energy gap here is in the UV to visible light spectrum. Right, and so it can absorb some visible light, and so this is where some of our colored organic compounds are going to come from, and the molecular orbital theory explains why they are a certain color. But we'll take a look at that more later on.